Welcome back. Today we'll dig further into the foundations of NLU by looking at word sense disambiguation, or WSD. WSD is a complicated way of saying find the correct dictionary definition of a word. All in all, cognitive scientists like me should be able to bet our life that our machines understand us most of the time. We can already play that game with banking systems because they are highly accurate. I believe that today, if you gave the big IT companies such a challenge, they just wouldn't bet. Lack of AI progress in NLU seems to stem from the science not being a sufficiently accurate model. By simply adding context and meaning, the combinatorial explosion becomes an interesting historical puzzle, not a showstopper for talking machines. So as we say, the meaning of a word in a sentence is determined by the meanings of the other words in a sentence. But on top of that, we then have to work out in context how those particular words also interact. So let's get into it. Human languages are not highly ambiguous. The words that we use at a particular level might be highly ambiguous, but as soon as you get to the sentence itself, in context, it's not ambiguous. So the secret of NLU is biting the bullet and resolving context. NLU makes no sense without context. It's probably worth just stating that again. Last time we looked at the man ran versus the water ran, where we saw how the word run is disambiguated, and then we're going to extend that into real language today, and we're going to look at some of the numbers that go into the computational linguistics model, which talks about astronomically large numbers, and then the functional linguistics model, which by breaking down the meanings of words into these components, we're able to vastly reduce the impact of the combinations used in language. So today, word sense disambiguation, or WSD, selecting those dictionary definitions is the key focus. So I've said this before, but leaving out context makes the problem of NLU too simple. It's simpler than it can possibly be in order to be effective. So here's our model. And look, there's our context on the lower right, syntax, which is the focus since the 50s on the lower left, and meaning at the top. So when you go from the syntax to the meaning, that's effectively like looking up the dictionary. So that's our word sense disambiguation step. And once you have the meaning and you start to recognize how that works in context, now you've got true context. And so for us, real context is all of the elements that take place at a point in time. So who, what, when, where, how, why. That's the key. So when you're reading a particular book, for instance, all of that knowledge is found in that book. So that's a key location for that particular information. And it's so important because if you were to, say, read things on the internet, so you listen to people's blogs or look at media reports, depending on who it is, you can get a completely opposite perspective. So one person can say, for instance, the president of some country is an idiot, and someone else can say he's a genius. It's not possible to resolve the truth behind that because in both cases they're just opinion, and the opinion actually comes from context of who said that particular fact. So here, let's just run through an example of how we use context to resolve meaning in conversation. If you started a brand new conversation with "he's happy," the obvious question would be who's happy, and then the answer would be something like this: Fred, or Fred is, or Fred is happy, at which point you know that he means Fred. If somebody were to say out of the blue, Fred's happy, and you don't know Fred because he's not currently in this conversation, the answer would be, that's Fred, or the man I saw, whatever, my friend from school. All of those give you some sort of knowledge about that referent Fred. But how this is working with role and reference grammar is whose Fred is the question form in English, where we're seeking information. So if you convert that question into a statement, the statement is Fred is who, and now we're substituting for who in order to get the answer. And historically, this next example, flying planes can be dangerous, is an example of structural ambiguity. And the way you would resolve that, if somebody said flying planes can be dangerous and you wanted to know whether it was the planes that are dangerous or the flying that is dangerous, you could say, what can be? And depending on what the person says, flying or planes, that's actually the meaning of that phrase, flying planes. And now, unambiguously, you know what's been said. Okay, so the combinations in science is another area that I just want to touch on because we keep hearing the big IT companies say, we just need more data. We just need a little bit more data. Well, the little bit more data is such an astronomically large amount of data that it's unsolvable. And if you think about it, you would never be making those types of claims. So, for example, Steven Pinker, a well-known cognitive scientist, one of the guys in my field, he pointed out in one of his books in the 90s that if you were to go into a library, open a book, the biggest library that you've ever seen, open a book at random and choose a sentence at random, the probability of finding that sentence in another book is pretty close to zero. Languages tend to be very variable in how we express ourselves, to the point where you can say a sentence and immediately target it to a particular movie or a particular event in your life, because that unique set of words, that sequence of words, is sufficient to identify the place. And then, as we said before, context comes in and you've got a lot more knowledge. So let's have a look at the formal versus functional linguistics another time, just to cover this in more detail. So the combinatorial explosion is what we tend to teach our young students, and then we tell them, hey, but you can solve it with statistics or neural networks, and then they're kind of locked into this model which is an unsolvable problem. NLU, that as we found through many decades now of working through the alternative design approaches, meaning is definitely the right model to use in order to deal with the varieties of words, word compositions and word orders that we see in languages. And plus we want to be able to learn by experience, and you can't imagine learning by experience by simply getting a book full of meaningless words. So the point of this particular slide is that meaning allows the pattern atom to take the elements of the word and learn by experience and to generalize, whereas these meaningless words, collocations, you can't imagine how you're going to be able to learn in real time, as people do. So here's our earlier example, the man ran versus the water ran. And if we now look at how we can generalize that by simply having that sequence, mammal and the manner is moving by legs, so that's the semantic representation of it. Now, if you go in the opposite direction to a man as a type of mammal, if you go mammals are, you've got cats, dogs, cows, giraffes, kangaroos, etc., etc. There's roughly 4,000 of those in the world. And any one of those is now immediately going to recognize moving by legs. You might need to change some of that. We've got in pattern theory techniques to do that. Also with, you can also generalize in that if a person is a mammal, then any of those other elements will also, because they're mammals, be connected up, and Bob's your uncle, we've got a solution. Data by comparison doesn't generalize. The idea first that you shall know a word by the company it keeps, in his particular example, it sort of made some sense. I don't think he would have in his wildest dreams said, well, you shall know a word by the company it keeps, so if we grab a whole lot of documents and then produce statistics from it, that's going to tell us what it means. No, sorry, don't buy it. And because there's no associations in data itself, because there's no meaning in data, it's just meaningless words, and then the statistics of them in particular documents, we got problems, man. And it doesn't seem to be scalable to me. When somebody uses, like a Siri or an Alexa, and it doesn't do what they expect, it's because of the vast amount of generalization necessary to work in the world with NLU. It's not a data problem because the numbers are too big. Now here's Professor Pustiowski's contribution. If you say a man began a sandwich, you actually understand that the man's going to eat a sandwich or make a sandwich, and depending on the context, you can resolve which of those it means. But possibly seeing the sentence, it's unresolved, and that's perfectly okay, because if you don't need to know the correct answer, then any answer is good enough. But because sandwich is an undergoer of eat, it's an indirect undergoer of eat, because if you eat food and a sandwich is a type of food, those two elements come together through the network and you're resolving them. So if animals eat food and food is the undergoer and sandwich is, there's your image. So with data science, it's not clear what a solution would be, even in theory, let alone in practice. So let's do some math. The man kissed the donkey. You've got mammals, kiss, mammals. Let's just say that's our first try. Again, pattern theory takes this to much deeper levels than this, but let's just illustrate the point. So we've got 4,000 mammals on both sides. Obviously, it's not two different groups of mammals. This isn't data as you would think of it. It's a network, so you're connecting to mammal, which in both cases is the same mammal that you're connecting to, because you can only store an atom once. So here we're going to add some elements. So notice that kissed is past simple tense. But you could say didn't kiss, so that's negative past. Does kiss, positive present. Doesn't kiss, negative present. Didn't not kiss, double negative past. So all of these are completely intelligible to normal people. So all of them need to be catered to by NLU. And then we'll just add one adverb or one additional predicate that's going to give us the pace of that particular first predicate, which is kiss. So if you slowly kiss, now we can have a number of different ways of adding that. But let's just say there's 15,000 forms of slowly, because again, language has a lot of words that we're dealing with. And bingo, there's our maths. It's showing 115 or 1.152, and then we've got 3, 6, 9, 12, 14. So 1.1 by 10 to the 14 combinations of that one particular sentence with some vast simplifications, right? The cat and the dog, obviously, you can describe those with whole sentences as well, which are going to have vast numbers of solutions. And with real language, you might say the man kissed the donkey. So slip of the tongue, you say no, and then replacement word. And bingo, you've now got a very meaningful sentence. But we can actually say the man missed the donkey, no, the bear, and equally you've recognized the difference. So it's not just the predicates that we can get confused with, it's also the reference, and in language there's no problem pulling all of that together. And so let's say there's 1,000 ways of doing that error correction. Right? So instead of just saying no kissed, you might say no, I meant kissed, or no, sorry, what I meant to say was. So let's say there's 1,000 of them. Obviously there's a much larger number than 1,000, but if there was 1,000 of them, and we now go from kissed to the different types of predicates that we could have. Again, we'll say 15,000, which would give us 75,000 word forms, because obviously there's more than one word form for an English word. That gives us 8.6, and let's see, 3, 6, 9, 12, 15, 18, 21. So 8.6 by 10 to the 21 combination. So it's a pretty big number of ways of saying that one particular simple sentence. And if corpus linguistics needs actual examples, if it's not generalizing very much, then for accuracy, you're going to need that number of samples in your input data, in your learning input. Now, yes, so the man began a sandwich. You can obviously say this in a lot of ways too. It was a sandwich the man began. It was a sandwich that the man began. Instead of began, we can have some other synonyms. Let's see, the man started in on a sandwich, or it was a sandwich the man started in on. All of these combinations, like there's a sentence, a sandwich the man had been beginning when the clock struck 12 was tasty. So all of that needs to be catered to by NLU. How are you going to do this with phrases? That's my question in data science. And note that the actual meaning eat isn't even specified. It's coming from that concept of qualia. So fundamentally, I think the science is flawed. Here's the formal language processing for NLP. We start with letters. We then convert through sequences of those letters. We create words and cat the act. Many, those are your terminal symbols, and then your non-terminals are effectively noun phrase, verb phrase, so those types of things. And then you have rules to manipulate it. That was the model put forward by Chomsky and by his predecessors going back to the 30s, where we're using these parts of speech in order to model language. So this is a formal linguistic model that I guess you would give Chomsky credit for. And it's been unsolved now for 60-something years. Notice, though, that the types of things for your grammatical rules you would need to deal with is the fact that the word slowly, if you were to slot it into that sentence, the tree has been growing, you could put it at the beginning of the sentence, slowly the tree has been growing, which is the left detached position according to Roland reference grammar, or those different positions in the sentence. We start to multiply out the number of different phrases that we need to track to an extremely large number. So yet another example of having very large numbers of things. All of those examples below, even if you say, it's not really syntactically correct, you wouldn't really say the tree slowly has been growing. It would a bit of a stretch, but you could say it. The point is, if you can understand it, then NLU needs to understand it. And we use two predicate phrases to recognize all of those cases. So the power of sets is far more powerful than the power of trees. And now here's our model. There's the formal linguistic system. It's basically bypassing all of the key elements used in functional linguistics. Now here's the functional linguistics that we embrace. Text in, or could be phonetic information coming in rather than written symbols, but you've got your input. You then recognize your words and phrases in language understanding. You go through to create your semantic representation, and then you validate it in context. And that's your NLU process, and then reverse NLG. It's simply going from the meaning through into your generation with words in sequence. Now, the interesting part was, when you really analyze it, the science causes the combinatorial explosion. So we've seen that parts of speech is a very ambiguous methodology, multiplying out the number of dictionary definitions we've got. But there's other types of dictionary definitions. So I'll just run through that really quickly. So with parts of speech, the eating of the burgers by the diners is the noun form. The diners ate the burgers is the verb form. The burger eating diners would be an adjective form. So we're able to drop off these extra definitions to get the effective same results in our system, but without all of those extra permutations we'd have to worry about. Equally, this form here. So if you've got the meaning of a predicate march, which is that there's this activity taking place by, in this case, the soldiers march by soldiers, that's a dictionary definition. But you can add a second definition, or second and third, as we see in WordNet there. If you said the sergeant marched the soldiers, that's now a causative form. But it's the phrase that determines the causative form, not the word. The word is actually unchanged. And you can see there that the sergeant does something which causes the soldiers to march. So you don't need an extra predicate in order to recognize that in NLU. So we can get rid of extra definitions. And here's another one. So if you enter a bank, which is a building, that's different from say, working with a bank, which is an institution. But based on the idea of Qualia, Pustiovsky's Qualia, you're then able to simply create an association in your semantic network, and you don't need the second definition. So there's an institution which happens to have branches, which happens to have buildings. So if you go to the bank, you're actually going to the institution and the building, and you've got to ask the question, do we want to disambiguate at that point to be absolutely certain whether we're dealing with the institution or the building at a particular point in time? My argument would be you don't resolve it until you actually need to. Okay, so where we're at is that we've looked at parsing with statistics. That's our state of the art. And then we've got this idea of word sense disambiguation based on tests. To me, the current tests are somewhat lacking, because what will happen is you'll get, say, a sentence, you'll have your training data, and then the idea is you're going to pick the third word and you're going to say, what's the correct word sense? The trouble with that type of system is, firstly, you're bypassing a key element, which is how do those words in the sentence relate? That's what you've got to do in order to solve the problem of NLU. You need to know all of the predicates, and then you need to have the disambiguated forms of the words in relation to each other. But secondly, the particular word sense, sometimes there's more than one, and you need to choose all of them. That's all. We've also seen that parsing is impossible, and the idea of more data when you start to talk about real language is just astronomically too big. Also, we know that children generalize from language. The brain is obviously learning language in a different way to getting every possible combination, because there's just not enough time in the universe for people to learn a language based on being exposed to every possible sequence. And I know the idea of machine learning is to generalize, but traditionally it's the marked up corpus, the annotated forms, that are really the element that holds those systems together. And by simply using the generalization, it means you don't need the corpus, because we've been building dictionaries for centuries. So it's not more complex to build a dictionary for a language today than it was a couple hundred years ago. In fact, it's easier now because computers make the process easier and more controllable. So we'll come back to this generalization when we have more time to go into detail. Just touching again, parsing doesn't work because the parts of speech is too simplistic of a model. It's the meaning of the words that you really care about. So why focus on an aspect of how that word was used in a sentence, a noun or a verb? So here, discuss dogs on the beach. In this case, Jurafsky's pointing out that, is it the dogs on the beach you're discussing, or is it discussing on the beach the dogs? It's not a solvable problem outside of context. And Google pointed out that this type of problem is exactly the ones that they're struggling with resolution today, with their world's best solution with SyntaxNet or Parsing with Parseface. Some more examples. The man began a Big Mac. The man tried a Big Mac. The man began to try a Big Mac. All of these elements have to be dealt with by NLU. If you park in the back, you're not parking yourself in the back, you're parking your car. So there's your have association popping up again. But let me just finish now with the state-of-the-art word sense disambiguation. This is an extract from a 2013 article, so it's 5 years old, but nothing's changed. The goal of WSD is to computationally assign the correct sense of a word. Now, why do you have to do it computationally? Because computational linguistics is building up these statistics, and then you've got to compute which of the statistics is the right one. But there's a predefined sense inventory. Obviously, in the real world, a machine needs to learn these senses in real time, because you can hear a new word and then work out what it means. It's not complicated with pattern theory to do that, as we saw with learning of a language. But here is the biggest problem with that test of WSD. You can see that example. The boy leapt from the bank into the cold water, and he says the edge of a river is intended just there. And my question is, why? Because you can think of an example where that's the wrong answer. So passing this WSD test is actually giving you the wrong answer in certain contexts. And anytime you look at context, you can work out a counterexample. So context is the only solution. So here's the example. If John jumped from the bank into the water, we saw in the benchmark test, you have to say riverbank. That's the wrong answer in this case. Okay, so the window to the lobby was open when the bank robbers arrived. The river was directly under the window. John, avoiding gunfire, took his chances and jumped from the bank into the water. And clearly, you're jumping from the institution, which has a branch, which has a building, into the water out of the open window. So the moral to the story is don't guess. Use of context is the only human-like model for NLU. So there we have it. Another view of NLU focused on the challenge of science. By simply embracing the problems we have known about for a long time and not compromising with interim solutions, the era of talking and interacting with machines naturally is upon us. I'll see you next time. This is John Ball, signing off.